to give me the opportunity to talk today. I'll be talking about a project that was mainly done by Roger Tier. He's now a former PhD student, just passed his Viva a couple of weeks ago. And it's on mitigating the climate impact of contrails by what we're calling small-scale flight diversions. I also want to acknowledge Ulrich Schumann at DLR for providing the contrail model and input into the project. So firstly, what are contrails? Let me turn that off just in case. Okay, so they're these line-shaped clouds we see following aircraft in the sky. Sometimes we see them really visibly and they last, and sometimes we don't see them at all. So what we have in the exhaust plume of an aircraft is some soot particles and lots of water vapor. That water vapor condenses onto the soot particles, forming liquid droplets that then quickly freeze and into ice crystals. And so what we see as a contrail is a collection of ice crystals. The formation of the contrail we can think of in terms of thermodynamics. And so this graph here shows the partial pressure of water vapor as a function of temperature, and then the lines of saturation for water and for ice. And so up to towards the top right-hand side, we've got the exhaust conditions of the aircraft, very hot and quite humid, but too hot for water vapor to condense. And then as that cools, the temperature decreases. So as the plume cools and gets diluted, the temperature decreases, the partial pressure of water vapor decreases. But if the plume cools in such a way that it crosses the saturation line with respect to water, then you can get condensation of water onto the soot particles. So in this pink line, the plume cools in such a way that no contrail is formed. And in the yellow line, you get an initial formation of these droplets and a contrail, but then it doesn't persist because the conditions in the atmosphere are such that those ice particles would then sublimate. But then if we have this green line, then this would be an instance where a contrail would form and then it would persist because the conditions are such that it's saturated with respect to ice, and so those ice particles can remain. And so we typically think of threshold conditions where you need to have exceeded the supersaturation with respect to water for those initial droplets to have formed, and then they can either persist if the conditions remain supersaturated with respect to ice, or they can be short-lived contrails. And if they persist, they can spread and cover really significant areas, and they have a radiative effect. So just very briefly, the radiative effect is that contrails can reflect incoming solar radiation, so they reduce the amount of solar radiation making its way down to the surface of the Earth. But they can also trap outgoing long-wave radiation. And clearly during the daytime, it's a balance of these two effects, but at nighttime, the cooling effect of reflecting sunlight back out to space goes to zero, and you're left with this warming effect of trapping outgoing long-wave radiation. So the radiative forcing of contrails and contrail cirrus, as those contrails spread, we call that contrail cirrus, is comparable to the radiative forcing of aviation's cumulative CO2 emissions. So that means all of the CO2 emissions emitted by aircraft from the beginning of time. So it's a really significant component, but it does have a higher uncertainty. Okay, and not all contrails are created equal. So firstly, not all flights form contrails, and then the contrails that are formed, they may last for only a few seconds, or they may last for several hours, and that will depend on meteorological conditions. They're also dependent on the engine particle emissions, also diurnal and seasonal cycles, and also on the surface over which they're covering, so the surface albedo. In terms of contrail mitigation, people have thought about alternative fuels, which have shown to reduce the number of particles emitted by engines. This can be somewhat offset by an increase for some biofuels of the water vapor emissions index. People have also considered flight diversions, but you want to be really careful about diverting around areas of the atmosphere where contrails would form, because that could lead to additional CO2. And then people have also thought about cleaner burning engines, and that's what these two final things are what we considered in this study. So diverting flights above or below contrail forming regions, as shown in the diagram on the right-hand side, and also assessing the effect of cleaner burning engines, so reducing the number of soot particles emitted per kilogram of fuel burned. Research method is that we took an aircraft activity data set for Japanese airspace. Using that, we predicted fuel consumption with also input of meteorology. From fuel consumption, we estimated emissions of black carbon particles and CO2. We fed the emissions and meteorology and radiation into a contrail and radiation model, so that's called COSIP. And then using those results, we were able to evaluate mitigation strategies. And one thing we've done within this study is use a Monte Carlo approach to account for the uncertainties that you have both in the emissions, but also in the meteorology. So in other words, the weather conditions. So this emissions index, EIN, represents the number of particles emitted per kilogram of fuel burned. And to estimate that, in this study, we've used a fractal aggregates model that I've spoken about at a previous Cambridge Particle meeting, and we published last year. Essentially, this relates the number of soot particles to the mass of soot particles. In doing so, it uses this is the mass emissions index, the size distribution, the particle size distribution, so the geometric mean diameter, geometric standard deviation, the mass mobility exponent, and KTEM and DTEM describe the relationship between the primary particle size and the mobility diameter size, or the aggregate size that's been observed in the literature. So this model has been validated on several types of black carbon sources, including aviation soot, and we can propagate uncertainties in all of these parameters, and that led in this study to this uncertainty distribution on the bottom right-hand side, showing a sort of asymmetrical distribution with a 95% confidence interval around the mean of -70 to plus 200%. So one thing about contrails is that they're on the whole, in general terms, very short-lived. So they last for about a day maximum. And so to quantify the radiative effect of that, we've used a metric called the energy forcing, which has units of joules, which sort of describes the amount of energy trapped or that doesn't make its way into the atmosphere as a result of the contrail. So it's the radiative forcing, local radiative forcing of the contrail multiplied by the length and width of the contrail integrated over the lifetime of that contrail. And we want to compare that to the energy forcing of CO2. Now, CO2 has much longer lifetime in the atmosphere of several hundred years. So in order to do that, we take a similar approach, but we use the absolute global warming potential over a given time horizon. So that's what TH is, a time horizon. And for the results presented in this presentation, I've taken a time horizon of 100 years, but we also show the sensitivity to taking a time horizon of 1,000 years. If you go to a longer period of time, then clearly the impact of CO2 becomes dominant over the impact of contrail. So in terms of results, this shows these figures shows the total number of flights forming contrails on the top, the net radiative forcing second down, and then the third one is the contrail energy forcing. So in our data set, 17 or 18% of flights formed contrails with a mean contrail segment age of about 3 hours. The pattern that you observe is a result of both meteorology, but also the sort of diurnal pattern in flights. So we see a peak every day. The gray area represents the confidence interval. The blue line represents a estimate if we were to use a constant emissions index, emissions index. And you can see that it lines up pretty well with the black line, which is using aircraft-specific emissions indices for black carbon particles. So the net RF is positive, which means it's an overall warming effect. And then the total contrail energy forcing is of the order of 5 × 10⁻18 joules. So because we're estimating the contrail of every flight, we can then rank these flights in order of their contrail energy forcing. And if we do that, then we end up with a graph that looks like this. And this shows the cumulative contrail energy forcing on the y-axis. That's it. X-axis is only a small percentage of flights contribute to most of the contrail energy forcing. So in this case, 2.2% of flights account for 80% of the total energy forcing. So this was a really important result for us because it meant that when we're considering mitigation of contrails, we don't need to consider diverting all flights or changing the altitude of all flights. We can actually just look at a very small proportion of flights and do something about them. So the other way to read this is that the majority of flights don't actually form meaningful contrails that have a sort of significant warming effect. So it is a very small fraction of flights that cause these warming contrails. So another thing to consider is that, as I mentioned earlier, you need the right atmospheric conditions for contrails to form and to persist. So these figures show the relative humidity across the domain at 3 different flight levels. So flight level 340, 360, and 390. The green dots indicate new contrails and the blue dots indicate persistent contrails. And just for reference, the air traffic density is roughly the same in these 3 different pictures, but we do see significantly different amounts of persistent contrails between the 3. So you can see the sort of lower amounts of blue dots in the left-hand side. And so this is showing us that these areas of the atmosphere which are supersaturated with respect to ice are relatively thin. So that led us to think, well, we could make very small changes in altitude, cruising altitude, which could lead to significant differences in contrail coverage area and lifetime. So if we look at the most warming contrails, this figure on the left-hand side shows when those flights took off in terms of Japanese local time, and on the y-axis is the total contrail energy forcing, and so the flights with the most warming contrails take off in the late afternoon or evening, and it means that if they were to form a persistent contrail, then that contrail can last into the night and throughout the night. So our approach is to divert these flights with the largest contrail energy forcing and just look at changing the altitude of cruise by ±2,000 feet, and then changing the cruise altitude to the one with the lowest contrail energy forcing. And if we do that, we find that diverting up to 1.7% of flights reduces the warming effect of contrails, or this energy forcing from contrails, by about 60%. The overall result is in the black, and then the result for the 6 different weeks of data that we have is in these different colors. And so it is sensitive to different weeks. In week 3, there was a prolonged contrail outbreak, so lots of flights were forming contrails, which means that to reduce the energy forcing from contrail, we have to divert more of them. Whereas on the left-hand side, the pink and the blue lines, those weeks, contrails were only sporadically formed due to the meteorology conditions. So only mitigating the effect of a couple of, or a smaller number of flights would have a bigger effect. So it's also important to consider the fuel penalty and additional CO2. For each of these diverted flights, we calculate that there's an average of a fuel penalty of plus 0.27%. And if you average that over all flights that occur, that equates to about 0.014% increase in fuel consumption. So a really small increase in fuel consumption. That's for two reasons. One, because we're only changing the altitude of a small number of flights, but also because we're making very small altitude changes. So we can compare that against having cleaner burning engines. And if you have a cleaner burning engine, you end up with less soot particles for the same amount of water vapor. That means you end up with, once that water vapor is condensed, you end up with larger droplets and larger ice crystals. They can sediment out quicker and fall through warmer areas of the atmosphere and therefore sublimate, and that affects the lifetime. But also if you have a contrail made up of larger ice crystals, then it would tend to have a lower optical depth and so a less of a radiative forcing effect. So comparing these approaches, a small scale diversion, diverting 1.7% of flights, changes or reduces the energy forcing from contrails by 59%. If we add in the CO2 over a 100-year time horizon, that gives us a reduction of about a third of the climate impact from aviation. And that's something that could be done relatively quickly just by making these small changes to the altitude of cruise. Comparing that to the second approach, which is using cleaner engines, that reduces the energy forcing from contrails by about 69%. Adding in CO2, that's a reduction of 42%. And we can add those two together to get a total reduction in contrail energy forcing of 92%. So that's really promising. What we've gone on to look at is what if we promote the formation of cooling contrails. Now, if we want to promote cooling contrails, that means we need to form them in the day so that they can reflect sunlight during the day. And so we've done some experiments where we try and just choose the altitude of a flight which would minimize the energy forcing of contrail. And in that situation, we end up diverting about 15% of flights. But it completely offsets the energy forcing from contrails and reduces the total impact from CO2 and contrails by 2/3. So to conclude, a fleet-wide diversion strategy is not necessary, as 2.2% of flights contribute 80% of the contrail energy forcing. Small-scale diversion of flights could reduce the total energy forcing of aviation for this domain by 36%. Actively diverting flights to minimize contrails could offset the, the total climate forcing by about 2/3. And we haven't really looked in detail at the sort of impact on air traffic management, but we think that this could be implemented in the flight planning stage so that this is accounted for, along with other considerations about how flights are planned to minimize the contrail warming effect. So thanks for listening. I'm happy to take questions.
Great, thanks so much, Mark. We have time for about one question. So if you guys want to raise your hand on the participant panel, I'll choose someone at random. And then for those who don't have their questions answered, just pop them in the chat and hopefully Mark will be able to answer them there. So I'll give you guys a minute or two if there are any questions to just raise your hand on the side panel there.
Yeah, happy to answer questions in the chat afterwards as well.
Yeah. I think, so no one seems to be brave enough to raise their hand on the side here. So to stay on track, we'll move on to the next speaker. So thank you so much, Mark. I really appreciate it. And, so sorry, Joel has a question. So Joel, let's see.
Yep, I've unmuted him.
Oh, great, thanks.
Hi, Mark, thanks for a great talk. My question is, to what degree you think these results might be specific to Japan's meteorology, because it will be when it's on the edge that you get contrails? Yeah,
so there's a couple of aspects to that. So it's dependent on the meteorology, but also the structure of the airspace. We've got some preliminary results which are for the North Atlantic. And you have very different structure of the airspace where you have these tracks going across the North Atlantic. the balance, so this 2% to 80% balance shifts slightly, so you don't have as much of an unbalanced equation there, and that's also because flights sort of tend to follow each other across these tracks. So these results I think show the potential, but clearly more studies are needed to look at what the effect could be in different regions.
Great, thanks so much. And if you guys have any other questions, just make sure to put them in the chat, and hopefully Marc will be able to answer them throughout the rest of today. So thank you very, very much. Marc?
Thanks, Molly.
Yep, thank you. So our next presenter is George Biscos from Delft University of Technology, and he will be presenting on the characterization and testing of miniaturized aerosol instruments for the use on board unmanned aerial vehicle platforms. So we will have Marc stop sharing his screen and George starts sharing his screen.